Okay, so welcome to this third talk of the morning. So next speaker is Hugo DUMINIL-COPIN from both Geneva and IHES. And you might have heard his name in the news recently. So without further ado, give you the chair. And
thank you very much. Okay, so there is a slight problem with the slides. So if I point like that, it doesn't mean I'm trying to connect to Mars, okay? I'm just trying that we pass to the next slide. And you are going to see there are many connections in my slides, unfortunately, so it's going to be a little bit intense for everybody. So I apologize, but I was told I have 30 more minutes, so that's good. No? Okay, good. So it's a very general audience talk. It's not intended to probabilists in particular, for the probabilists in the room. I'm going to try to give you an idea of our field of research, which is a study of phase transition in statistical physics. And I'm going to take time to actually explain to you, in particular, how you get to create a mathematical model out of a physical phenomenon. And I will try to give you an idea of a few terms. Here you have a certain number of them. So is this working? Ah, yeah. You have a certain number of terms that I will try either to explain or at least that I will shoot at you at some point, but just for a brief instance. Oh, it does connect. Okay, so let's start with the beginning, which is how you cook up a mathematical model. Okay, and I'm going to take a specific example. I'm going to take the example of the Ising model. So when you try to cook up a mathematical model, you start from a physical phenomenon. You start from a physical phenomenon. Yes, we get it. Very good. So, which I'm trying to illustrate here through an experiment. So you see a mathematician doing an experiment, which, by the way, it took me like ages to crack this element, this light. Anyway, so you heat a magnet, and what happens is that after a certain, when it reaches a certain temperature, it stops to be a magnet. So here you see it becomes a little bit weaker, for instance. But if you keep going and you keep heating it, at some point, it ceased to be a magnet. It's something that was actually discovered in the beginning of the 19th century by French physicist Fourier, but it was, let's say, put to a next level of recognition by Curie, who noticed that whatever the magnet you take, if you heat it, there is a temperature that we now call the Curie temperature, sorry. There is a temperature at which it ceased to be a magnet. Here what happened is that it became so weak that gravity called him back to the ground. Okay? So you have different values for different materials, but every single time, we are in Europe, so we use this one, every single time you have a critical temperature at which you stop to be a magnet. And the goal is to try to explain how mathematically why this happens. Okay, up to now, I think it's a fairly clear problem. It comes from physics, not from math. I chose a phenomenon that was coming from physics, but the modeling, of course, could come from a problem in chemistry, in computer science, etc., etc. Okay, so what's the first steps when you try to cook up a mathematical model? Well, the first step is to try to understand what is going to be the mathematical definition of your object of interest. And in this case, I'm talking about the magnet. So what is a magnet? Well, mathematically, we are going to say, we are going to borrow from the physical interpretation. A magnet is made of a collection of small dipoles that kind of act like small magnets. These dipoles, we will say that they have a magnetic moment. We call it sigma x. We call it the spin because there are actually connections to quantum physics, but it's not, you should not think of the spin of an actual particle a priori. But let's do that. And now, once you made this first assumption or this first description of your magnet, you want to kind of make assumptions that are going to be allowing you to work with your object at the end. So we are going to follow something from Mark, which is that we should be wise and discretize, and we are going to do two discretizations. I'm sorry about, I'm trying to be focused, but it's not easy for me. So first discretization, we are going to assume that our dipoles are actually regularly spaced on a lattice. Okay? So for instance, here's a square lattice, but if you want to be thinking of something that is modeling a three-dimensional magnets, I mean, magnets are three-dimensional objects, think of the hypercubic lattice. You could think of other lattices in 3D, but for us, it will be as good as we can to actually work with the hypercubic lattice. So that's the first discretization, is discretization in space in some sense. The dipoles are regularly spaced. The second assumption is that, the second discretization is that why you could think that the magnetic moment of each dipole would actually be pointing in any direction. Here I'm going to make an assumption that it's actually pointing out of two opposite directions, say north-south or up-down, or we are mathematicians, +1, -1. Okay, so we are going to assume that the spins, it's super nice here. It's, you should all come and it's much nicer than upstairs. So anyway, is it a tentative to make mathematicians come forward in? Okay, well, so sorry. I'm not really sorry, but so anyway, so the spins are pointing plus and -1, and now you have what we call a magnetic, a mathematical magnet. It's just going to be a function from this portion of the lattice into ±1. Okay, that's the object. Okay, up to now, we just described what a magnet is, but you can definitely see and guess that a magnet is made of a huge number of small dipoles, so it's going to be very difficult to describe it well and in full precision. So what we are going to do is that we are going to introduce randomness to, oh, no, we are not going to introduce randomness, sorry. I'm going to first tell you what is the strength of your magnet, sorry. So the strength of a magnet, sigma, is going to be kind of how much it is aligned with up, which you can measure by looking at the average spin on the magnet. Okay, that sounds like a very natural way of measuring how much it is aligned with, say, up. Okay, so now I'm going to what I was saying, that it's a complicated system, and therefore you want to introduce randomness to be looking at kind of the typical behavior of your mathematical magnet rather than looking at the actual full description of the magnet. So in order to introduce this randomness, you do what we always do in statistical physics. You start by trying to describe what is the energy of a magnet, how energized it is. And the first thing that you can notice is that if you think of your, ooh, it's cool, if you think of small dipoles as being kind of small magnets, what you know is that magnets have a tendency to align. So in particular, it's going to be more costly if two magnets disalign rather than align. Okay? And here I'm going to make an assumption again. So, you know, I'm piling up assumptions in some sense, but I will come back to this later on. I'm going to assume that the biggest interaction is between neighbors. So I'm only going to focus on how... That's me? Oh, okay, sorry. I speak very loudly anyway, so people in the room will get the full talk. So, so you want to look at how aligned the neighbors are, and one way of doing that is to introduce this global energy here, which is going to take into account, here it's just, if you want up to a constant, which for an energy is irrelevant, it's just the number of neighboring pairs of vertices that disalign. Therefore, the more alignment I have between pairs of neighbors, the smaller the energy. And what we do is that we follow Boltzmann or Gibbs, and we say now the probability of a configuration should be lower if the energy is larger, and the right way of putting this mathematically is to say that it's proportional to exponential of minus the energy times a factor that is taking into account, if you want, the intrinsic excitation of the system, which we interpret as 1 over the temperature. Okay, so when the temperature goes to infinity, you are pointing to only, like, there will be only 2 configurations that have a positive probability, which will be all aligned up or all aligned down. So you really want what we call the ground states of your system, what are the magnets that minimize the energy. On contrary, when t goes to infinity, did I say infinity? I meant 0. Sorry. When t goes to infinity, then 1 over t is 0. So here you only take a uniform magnet. You disregard completely how neighbors have a tendency to align. And in between, you have something more interesting when you care about the energy. So there's going to be a competition between the energy. You still want to kind of minimize it, but you also have an entropic term that many magnets have the same energy. So there is going to be a good balance between the two. Okay, so as I said, T is here interpreted as a temperature. So that's called the Ising model. Now you have basically the two ingredients of the Ising model. You have the definition of your your mathematical magnet, and you have the way you sample it at random according to this probability measure. And here again, you can try to measure, if you want, the magnetization of your magnet. Now it's a random magnet, so you are going to take the mean of the magnetization of each magnet sigma with respect to your measure mu. And here what you notice immediately, it's very simple to observe, is that a magnet and its full opposite, where you reverse all the dipoles, they have the same probability. So therefore, when you plug actually the mean magnetization, what we actually call just the magnetization, you get 0 at every temperature. So in some sense, you are not really measuring here whether you would be an actual magnet or not. So this we don't like so much, and we are going to complexify. That's going to be the last step of our French cuisine to get to the model. Actually, it was more a German cuisine because it was invented by Ising and Lenz. But what you do here is that we are going to break the symmetry between up and down that we had cooked up, in some sense, a little bit arbitrarily. So in order to kill this symmetry, what we are going to do here is we are going to force the boundary here to be all up. Let's say the black are actually up. So you should interpret this, even if it's not such a good interpretation, but for this talk it's going to be sufficient. Interpret this as you are putting your magnet in a magnetic field, which is forcing the boundary to actually align with the magnetic field. It's not an ideal thing, but for the sake of this, this talk, I think it will be fine. So you do that. And once you have done that, you can cook up a new probability measure, this time with what we call plus boundary conditions, which is exactly the same, except that here, if you want, you have two ways of thinking about it. Either you are favoring here on the boundary that the spins are plus, or another way of putting it is that this measure is defined on magnets which are conditioned on the boundary to be plus. And it gives you a new measure, mu plus. And the advantage of this measure is that when you look at the mean, in fact, as you can kind of guess here, you see that there are more pluses than minuses. So in fact, when you look at the mean magnetization, you get something strictly positive in this case. You have to prove it, but it actually, it is what happens. So very good. Let me give you the last ingredient, is that we are looking at a magnet, so it's a huge collection of dipoles, and as we are mathematicians, we are allowed to do something that physicists are not always allowed to do, which is pass to the limit. So if you take a bigger and bigger magnet, if you want, you can look at the mean magnetization, and it will converge, in fact, to a quantity in the limits when you took the limit of your magnet to the full ZD. This quantity here, it's called the spontaneous magnetization, and notice that you start from something strictly positive, so you will end up with something which is non-negative. And here the main question is exactly going to be, is it strictly positive, which would mean that we have a real magnet in front of us, or is it 0, which means that we lost, in some sense, the symmetry breaking in the limit, and we are in what we call the paramagnetic phase. So here, just one thing to keep in mind, we are taking the infinite volume limit. When there is a phase transition in statistical physics, it's always for infinite systems. Okay. So first recap. We started from a physical phenomenon, and it led us to a mathematical model by assuming some simplifying features. We had this B-wise discretize, and we have like we made the assumption of introducing randomness and then taking the infinite volume limit. Let me say that this is not at all something isolated to my research. It's a whole branch of mathematics that is doing that. Let me give you a few examples. For instance, when you look at interface growth of a real system, you can cook up particle systems that we say are in the KPZ universality class. This is one way where one place where again you will follow in some sense the same steps. You will discretize, you will introduce randomness, and usually take large-scale behavior, so take the limit when the size of the system goes to infinity. There is also other things. For instance, if you look at the kinetic theory of gas, you can cook up what we call the hard sphere gases. There are very beautiful works in recent years in these things, in this area. Or, for instance, maybe a little bit less obvious, but if you want to understand what happens in the nuclei of heavy atoms, in fact, the behavior of the particles in this are related to the eigenfunctions of random matrices. For instance, this was observed by Wigner, and it led to a whole area of mathematics called random matrix theory. So again, this was just to give you an example that this is not an isolated case. Okay, I try to just give you an example, but this is something very general in mathematics. And what did I say here? That's a good question. Oh, here. The model exhibits, so yeah, what I wanted to say here is that one of the interests of these models is not only that they describe physical phenomena. I would say that this is maybe how they are born, but from my point of view at least, the key point about this object is that they are very rich mathematical objects that actually connect to a whole branch, a whole bunch of different mathematics. Okay, so think of this as a motivation, but then the Ising model is a model of interest on its own, and you can forget actually the motivation, especially that if you speak to a physicist, actually what I told you is a little bit wrong. The Ising model is a terrible model for ferromagnetism, and I'm going to get back to this in a second. Okay, so now second part of the talk, what we will study here. So now we have our model, we would like to be explaining the experiments. And the first thing that you want to be explaining is whether there is a phase transition or not in my system, meaning a phase where you would have a magnet. So this would be the phase where m star of t is strictly positive. Yeah, very good. So that's what we call the ferromagnetic phase. And a phase where the spontaneous magnetization is 0, which we call a paramagnetic phase. Okay, so this is above the Curie temperature, and this is below the Curie temperature. And there is this special point, the critical temperature, where you have the phase transition occurring. Okay, so do we see that in the Ising model? We see it in nature. When you look at your experiments, this is exactly what you see. Do you see it in your mathematical model? Okay. So let me give you a little bit of history, because it's actually a pretty interesting history, and it's also a good example of what happened in statistical physics in general. So it started very poorly. Yeah, very good. So it started with Ernst Ising in 1925. Basically, he took over an idea of his advisor during his PhD, so Lenz. People usually say that the model is Lenz model and not Ising model, which is a little bit wrong, because actually the first person to state the Hamiltonian was actually Ising. So in some sense, I think it's very fair to call it the Ising model. And what Ising did was something that was kind of shooting his own foot. He looked at a one-dimensional magnet, and what he proved there, and it's an easy exercise actually, is that the critical temperature is 0, meaning magnets don't exist, right? You are always in the paramagnetic phase. And that was a catastrophic news for the model, as Ernst Ising put it. So he discussed the result with his advisor Lenz and with Wolfgang Pauli. And there was some disappointment that the linear model did not show the expected ferromagnetic properties, and I think this is real understatement of what probably happened in the head of Ising at the time. It's much more than a disappointment. It's kind of a catastrophe. And after that, actually, Ising left academia to become a physics teacher. And he learned only very much later that the model actually became one of the most classical models of statistical physics. The second very bad thing that happened just after the introduction of the model is that Heisenberg introduced his model of ferromagnetism, where basically he replaced these classical spins, this just idea that the spins will be plus minus one, and by what we call a spin angular momentum of the electrons in atoms. And this is a much, much better assumption. So it led to a different model, the Heisenberg model. And this model was much more in line. I mean, you are not without knowing that in the 2030s, it's really like the explosion of quantum physics. And the fact that the Ising model didn't match at all, in some sense, with the development in physics on the quantum side was a catastrophe. So this model of Heisenberg is a much better model for ferromagnetism. So this, not only did we not see any ferromagnet here, but in addition, anyway, the underlying justification didn't seem right. So at this stage, you could even wonder why on Earth am I talking like more than 100 years later about this model to you, if it's such a bad model. Okay, it's not such a bad model in some sense. It's typical model in statistical physics, so there are some pros. The first one is that despite what Ernst Ising proved, in fact, in dimension larger than 1, so 2, 3, in fact, any dimension which is not 1, there is a phase transition. There is a paramagnetic phase, and this was proved by Rudolf Peirce, that for several reasons is probably the person who saved the Ising model from oblivion. And so he proved that's positive. Okay, that's very good. So at least there are magnets from the point of view of the Ising model. But the second thing that he did, which is maybe even more important, is that he noticed that several other phenomena that were trying to be modeled at the time actually were modeled by the Ising model. But there was a connection between these other models and the Ising model. So he noticed that the same model can explain different physical phenomena. And that, at least from the point of view of mathematics, it's a very reassuring feature that there is some universality type behavior. There is an interest in generalizing in modeling, because then you can explain several phenomena at once. So that's what probably kind of saved the Ising model, but what really made it enter history is another result. Oh, yeah. Okay. It's another result a few years later by Lars Onsager. And the result is saying the following. It's saying that if you are on the square lattice, in fact, you can compute things explicitly in the Ising model. In particular, you can get a formula for what we call the free energy, which, if you want, is the typical energy per unit of volume in your system. Let's not focus about the definition. What I only want you to understand is that there is an exact formula for the quantity. You can compute explicitly what happened. It's a tremendous achievement, one of the biggest achievements of the 20th century in statistical physics and, in fact, in mathematical physics as a whole. It's tremendously difficult mathematically. It's a really a real mathematical tour de force. It was actually published in 1944 and then improved upon the actual strategy was improved by Breuer Kaufmann in a joint paper with Lars Onsager in 1949. So there is like a very deep underlying mechanism that explains the fact that we can compute this thing explicitly. And they have made many different approaches to get to this result. Approaches that are based on combinatorics, on algebra, on analysis. I wanted to mention this because it shows a connection that the model naturally gets with other fields of mathematics. And this result was really what kind of connected this model that a priori are really just dealing with with a physical phenomenon. Just this type of results show how interesting they are on the mathematical side. By the way, just for your culture, there is this nice paper in 1978 called the 399th solution of the Ising model, which is a slight exaggeration, but not by much, in the sense that there are today like many different alternative approaches that lead to this type of result, to these exact computations. Okay. So at this stage, you can wonder why. How do I relate this to the key player I introduced before? I told you, what I want to be understanding is the spontaneous magnetization. So what's the connection with the free energy? There is no direct connection between them, but the techniques that led to the free energy actually were improved upon by Cheng-Ning Yang. He was a young mathematical physicist at the time, and he became later on one of the most influential physicists of the 20th century. It's the same from Young Mills, from Lee Young, from Young Baxter. I think many people, if they think enough, they will find actually a contribution of Young that is very close to what they do. Maybe I should not say that, but I recommend that you think about this question. So when he was young, he liked the Ising model, probably also when he was old, but he worked on the Ising model, and he computed the spontaneous magnetization on the square lattice again, and it has this form. So you see one of the things that you get immediately from this is that this is positive if and only if t is strictly smaller than this quantity. Okay? So you can actually, in 2D, you can compute explicitly the Curie point, if you want, the critical temperature. And you can compute explicitly the spontaneous magnetization, and you see in particular that there are some interesting exponents happening when you look at the shape of this. Okay, why did I tell you all of that? So I wanted to tell you that on the square lattice, there is something very special happening, and in particular, due to this notion that I will not discuss more, which is called integrability, you can compute everything explicitly. Very good news, and that's probably what made the Ising model so successful, is that you can compute things explicitly, so you get a model for a physical phenomenon where you can compute things. Okay, but at this stage, we know there is a phase transition. We understand very well what happens at in 2D. We actually even compute the critical points. What do we do next? So the next question is to wonder what is the type of the phase transition, because phase transitions, they come in two kinds. There are the discontinuous and the continuous phase transition. So let me give you, as a good mathematician, I will start by giving you a counterexample. So what is not a continuous phase transition? So what is not a continuous phase transition is, for instance, the phase transition between water, liquid water, and ice. There we know that when you reach 0 degrees, just the volume of water changes when it gets to ice. There is a blow up by 20% or something like that, and it can actually lead to these explosions. But I mean, don't try this at home, and managing to get this picture is actually kind of not so easy. I think you have to really get to very small temperature to have this instant explosion. But anyway, it's a discontinuous phase transition. When you look at the Ising model, you don't get at all this. If you look at the graph of the spontaneous magnetization that was plugged by actually Curie, you see that something continuous is happening. When you reach the critical point, you get continuously to 0. And in fact, if you look at 2 dimensions and you look at the exact value for the spontaneous magnetization, you get something continuous again. So in phase transitions, in magnets, you get something continuous. Okay, so in 2D, you get it from the exact formula, but what happens in higher dimension? Well, in higher dimension, one of the important things is that you lose integrability. I mean, I have to be careful when I'm saying that, because of course, as long as you didn't, I mean, it's not so easy to prove a no-go theorem that really it's not integrable. But let me put it that way, it seems very unlikely that it is actually integrable in the sense that you can compute something explicitly. And even physicists don't manage to find integrability there, so it's a very strong indication that the thing is not integrable. So you don't have exact formulas. In particular, you don't know what TC is. You cannot compute explicitly TC. But still, you want to be proving that what happens for magnets happens for your mathematical model, you would like to prove that the phase transition is continuous. And so this is the first theorem that I wanted to mention in this talk. It's a theorem by Michael Eisenman, myself, and Vladas Sidoravicius. And it shows exactly that the spontaneous magnetization is 0 at the critical point. Again, we don't know what the critical point is. It's kind of defined implicitly if you want. But still, you can prove that the spontaneous magnetization is 0. And once you have that, in fact, it's just a corollary that it's actually continuous. So the difficulty is to prove that at the critical point, you have 0 spontaneous magnetization. So this was, as I said, a work with my 2 collaborators. And now I want to tell you a little bit where this comes from. Of course, I'm not going to give you a full proof, but I want to give you kind of an idea how you get to this type of results, because I think it actually gets to some nice feature of statistical physics. Okay, so the idea of the proof. So first thing, we are going to mention a new family of players in the game. So up to now, we only discussed the spontaneous magnetization. Now let's discuss spin-spin correlations. So what are the spin-spin correlations? They are, if you want, the correlations between 2 spins in my magnet, how they interact with each other, in particular, how much they influence each other. Okay? So you look at the average of sigma 0, sigma x. It has this formula, but I mean, if you prefer, it's just you take your measure and you look at the average with respect to the measure. Of course, as usual, you take the limit when lambda goes to ZD. I'm not going to tell you why it's well defined. Just trust me. I mean, this is not something that is going to be interesting at the level of this talk. And ideally, we would like to be understanding basically the large-scale properties. So how does this type of quantity, behaves when x gets to infinity, when they get further and further away. And the first thing you can look is that here I put this Diez type quantity because you could look either at the measure with no boundary condition or at the measure with boundary condition. And if you look at the plus boundary condition, what you get is that the spins, when they get further and further away, they act kind of independently. And if they act independently, then you basically get that their correlation is the square of their average. I mean, it's the product of the averages, and there are 2. So you get spontaneous magnetization squared. If you do the same with free boundary condition, when you don't have the plus, in fact, you can get 0 here. It's not completely straightforward. It's based on what we call the infrared band. I don't want to be discussing it too much here, but you get 0. Very good, because if you combine the 2, you kind of think, okay, then so here it's at the critical point. Here it's for every temperature, but here it's at the critical point. Then you deduce that the spontaneous magnetization is 0. So it seems like it's not even a theorem, except, of course, that there is a catch. And this catch is that there is here a plus and here nothing. So a priori, I need to prove that the free measure here and the plus measure here are the same, basically. And this is actually the whole difficulty. So up to now, I didn't say anything kind of smart. Oh, hello, that's cute. Very good. So at least he will be able to say that, you know, already at age 7 or 8, he was following my talks. It's a little bit scary. Okay, let me try not to traumatize anybody in the room. So how do you do to prove that these plus and free states are the same? Let me make a small detour. We did a bunch of, little bit of proof, so I want your brain to regenerate. And I'm going to do a detour by telling you about another of my interests, actually my main interest, which is called percolation theory. So what is percolation theory? It's a theory of random graphs. You take, again, you say the same lambda, so a piece of ZD, and you pick a random subgraph of this graph. Okay? You have tons of ways of doing, but for instance, keep in mind the simplest way, which is you take, for every edge in my graph, you color it in red with probability P, and so it's a lot to follow, but not to give the talk. Otherwise, I will really feel bad. So, okay. So every edge is turned red with probability P, and gray with probability 1 minus p. Okay? So you get a random subgraph, and in particular, you are interested in the connectivity properties of this random subgraph. And let me give you two nice pictures here. So what are these pictures? Here there are colors which correspond to the connected components of my graph. So I color in different colors the different connected components of my graph. And here, this is p equals 0.49, and here 0.51. And you see, just by changing a little bit p, you get a completely different behavior in what you see, in the sense that here you get something where there is a huge connected component in red that is basically invading the whole space, while here, if you think about it, the largest connected components are quite small compared to the size of the box. Okay? So this is actually a phase transition again in percolation theory between a p smaller than pc regime and a p larger than pc. This pc is distinguishing between a phase where there is an infinite connected component almost surely and a phase where there are no infinite connected components in my graph almost surely. Okay? Let me mention just the motivation for this model. It's to actually understand phenomena of porosity. Imagine you have coal, for instance, and you are trying to see whether a gas is going through coal or not, depending both on the size of the molecules in my gas and also on the temperature of coal. By the way, so this model was introduced by Broadbent and Hammersley after the war, but there was an interesting thing noticed by Mendes Ulamara, my former PhD student, is that Rosalind Franklin, who is also, you know very well from the discovery of helicoidal structure of DNA, actually did early works where she exactly looked at coal and tried to see how, depending on the size of the molecules and the temperature of coal, what gas was percolating through coal or not. And you really can think of this as early works on percolation theory. Of course, she was not doing like the mathematical modeling that consists in thinking of coal as a random maze, as a random graph, but it's maybe one of the first experiments on percolation theory. So I wanted to mention this cool anecdote to you. Okay, so what's the connection between percolation and the Ising model? The connection comes from the fact that you can actually rephrase the correlation in the Ising model in terms of a percolation model, so a model of random graph. So there is a way of sampling a random graph in such a way that in some sense, you can encode graphically the correlation in the Ising model in terms of connectivity properties of the random graph. More precisely, it's called the random current representation. It was introduced by Griffiths and then studied by many people, among which Michael Eisenman, that was one of the key players in this area. And one thing that you can do is that you see the spin-spin correlation between 0 and x, you can encode it for this random graph as a probability that 0 is connected to x in the graph. But you can do, in fact, much more than this. You can, for instance, compare the correlation with plus and the correlation without plus for the spin-spin correlation. The difference is going to be the probability that 0 and x are connected to infinity. I'm giving you that. I mean, you have to trust me, but you can encode, in some sense, the correlation in terms of random graphs. But one thing which is cool is that this percolation model, which is not at all Bernoulli percolation, it's a much more complicated way of sampling your random graph, it still has a nice property of percolation, which is that when there is an infinite connected component in the graph, it's unique. So in particular, if 0 and x are connected to infinity, they must be connected to each other. But that means that this term here is smaller or equal to this. So it's not true that the plus and the free state are a priori equal, but what you can prove is that the plus state is smaller than twice the free state's correlations. But this is very good because remember that we said that if you don't have a plus here and you let x go to infinity, this quantity tends to 0. While if you look at this guy and you let x go to infinity, it converges to the spontaneous magnetization. So what you just got from that is that the two things are equal, meaning the spontaneous magnetization is 0. So I lied in several instances, but I'm allowed to do that. But what I wanted to give you is this idea that sometimes you have connections between models that are actually explaining completely different physical phenomena, but when you get to mathematics, then the connections emerge. And in particular, once you have kind of discovered that the connection is very powerful, you can actually translate in the language of percolation a difficult problem in the language of Ising into a very simple problem. In fact, here, once you have this connection, the proof here, I mean, turning this wrong argument, because I lied in several places, into a full proof is actually not such a difficult thing. Okay? So the connection is very useful between the two, and I have no clue what time is it. 15 minutes. Okay, very good. So you are still mine for 15 minutes. Very good. So let me get to the second recap, and then we are going to dive into another interesting thing of statistical physics. So first thing is that the phase transition of Ising is indeed continuous, exactly like the physical phenomenon that it describes. In 2 dimensions, you can use integrability. Very good. And in higher dimension, you need to use another tool, maybe something that I would dare to call more robust, even though one has to be careful with this, but a robust tool, which is a connection to percolation models. And just for your interest, and also because here in Grenoble there are many people who love percolation. So let me mention 3 models of percolation. Actually, percolation come in many different kinds. I mentioned percolation, Bernoulli percolation, which was sampling the edges at random. I mentioned this random current representation that has nothing to do with percolation, Bernoulli percolation. It's a second example. Let me mention 3 others. So there are continuum percolation models where you can, for instance, sample random balls in the plane, and then you try to look at the connectivity properties of the random set you obtain. One model that I like very much is called the Fortuyn-Castellan percolation, which is a dependent percolation model where the state of edges are dependent. And you can also look at a random function and look, for instance, where it's larger than 0 or larger than a certain parameter, and you can get very cool percolation models. I'm thinking of Hugo Van Wil, who is here, and that likes this type of models. For instance, you can take, and Vincent Beffara, so you can take random spherical harmonics, for instance, and you can cook up nice models out of it. Okay, that was for the second recap. Let me now tell you about the last part of the talk, to give you an idea of a very cool phenomenon that appears when you look at statistical physics model at a continuous phase transition. In some sense, you still, you zoom in, you go further and further in your understanding of the phase transition. You prove there is one, you prove it's continuous, and once it's continuous, you start to have a whole story that starts to unravel in front of you, and that's what I want to be discussing here. So the idea is that if you look, for instance, at spin-spin correlation, so let's say now you look at correlations between not 2, but like 2 endpoints, okay? Or endpoints, actually, you don't need, I'm taking even because this measure is still flip symmetry, so if you take odd, it's 0. Take 2 endpoints, and you want to understand how these things behave. And what is going to happen is that when you tune the parameters correctly, so when you look at the critical point and when you look at points that are farther and farther away from each other, you have emergent laws, meaning laws that are not true in the discrete. When you look at your system just in a normal box or something like that, you don't see these laws. But when you tune properly, exactly like in philosophy or in physics, when you tune the parameters properly, then you have new laws that emerge, that are not apparent at this discrete level. And I want to give you an example of this through one specific example, which is the case of the Ising model in dimension 4. Okay, so first emergent law is that if you want to be studying the 2 endpoint correlations, in fact, when you are in dimension 4 and at the critical points, then the 2 endpoint correlations, they can be rephrased in terms of the 2-point correlations through what we call the Wick law. So what is the Wick law? It's a law that is satisfied. Here it's only an equivalent, which means that this divided by this tends to 1 when I take points that are further and further away. If you have an equality for every point, you get what we call a Gaussian process, which is one of the most classical process in probability theory. So what I'm saying is that asymptotically, if I look at critical Ising model, I get something which looks like a Gaussian process, which is one of these very simple random processes. So you get this additional property that emerges when you look at points that are farther and farther away, again at criticality. So this is a result that is actually true also in dimension larger than 4. It was proved independently by Eisenman and Fröhlich in 1982. And the rate of convergence in this equivalent here was actually polynomial in the distance between the points. Here, in dimension 4, you get something which is the power of log. It's what we call a critical dimension, and this is also why it took 40 years to get from dimension larger than 4 to dimension 4. So you can wonder why you are interested in dimension 4, because dimension 4 is the dimension of our Minkowski space, right? It's 3 space dimensions and 1 time dimension, and in fact there is a deep connection between the Ising model, or let's say one of its cousins called the 5-4 lattice model, and actually 5-4 theory, which is related to quantum field theory. If you want to construct rigorously a quantum field theory, you can try to start from a lattice model like the 5-4 lattice model and try to cook up your quantum field theory out of it. And what this result is saying is that there is almost no battery left. That's a harsh way of telling me to just stop my talk, but I was expecting somebody standing, not... Okay, anyway. Oh, it disappeared. Oh, that's fine. So what I wanted to say is that the theorem is actually saying that everything you will cook up out of the 5-4 lattice model or the Ising model will actually be what we call a trivial quantum field theory, meaning a quantum field theory that is describing particles that don't interact with each other, which fortunately for all of us, otherwise we would not be here, particles do interact together, so it's not interesting from the point of view of physics. That's what this theorem is saying. It's kind of a no-go theorem from the point of view of constructive quantum field theory. You cannot use the Ising model or it's causing the 5-4 model to construct an interesting quantum field theory. You have to go further to gauge theory and things like that. But what is the bad news from the point of view of quantum field theory? I mean, a no-go theorem is never what you really want to get. Is actually great news from the point of view of the statistical physicist, right? Because it means that if you, in order to understand the two endpoint correlation, you only need to understand the product, I mean, the 2-point correlations, because through the Wick formula, you can rephrase the two endpoints into the 2-point correlations. Okay, so now what I want to be, oh, no, that's not the right direction. So from the point of view of, yeah, you can go past this whole slide and get to the next one. So what I'm gonna try to explain to you in the end of this talk is how, thank you, how other emergent laws actually appear to help you computing the 2-point correlation. And if I tell you what is the 2-point correlation, I kind of describe the whole system because the two endpoints are now expressed in terms of the 2 points. Okay, so let me tell you now a story that physicists like to tell you, and which is a beautiful story. It's a story of renormalization. So it's going to be way too short, and it's not going to give sufficient credit to this discovery, but I want to give you an idea of what happens. So Leo Kadanoff, in the 60s, suggested that, oh, it's cool, there is some interference. So suggested that if you look at the Ising model and you divide your lattice into blocks, you can do what we call a renormalization by doing the following. In each block, you just take the majority spin. So you look at if there is more up than down, and you, yeah, very good. And you replace all the spins by one big spin, which is pointing up, if there are more up. You do the same with each one of the blocks, and you get a new model that then you rescale. So you rescale to the new thing, and you get, basically, you started from a model, the Ising model, and you get to something that looks like the Ising model again. And the idea of Leo Kadanoff is that actually this rescaling operation is kind of starting from an Ising model and giving you a new model, which is also an Ising model, just maybe with different parameters. But what happens is that when you start at the critical point, you stay at the critical point, and when you iterate, you should converge to a fixed point of this renormalization. So this is a cool idea, but as Kenneth Wilson put it in this quote that I learned from Roland Bauer-Schmidt, in short, the kind-of picture, although absurd, will be the basis of generalization, which are not absurd. So I think absurd is maybe a little bit too physicky for me. You know, physicists, they fight a little bit more than mathematicians. So in mathematics, we will call it naive, maybe, or something like that. That indeed, I mean, it's maybe too much to ask that this rescaling is giving you again an Ising model, but like all good ideas, you can turn it into something better. And Kenneth Wilson, what he said is that, in fact, what you should think of is that there is indeed a rescaling map when you rescale a lattice where you have a model on it. You are kind of applying a map on the space of all models. Maybe you start from an Ising model, you don't end up with an Ising model, but you end up with another model, and you can iterate like that. And again, you should get two fixed points, but then these fixed points, they should naturally be models, if you want, that are invariant under scaling by construction in some sense. So you should get what we call an emergent scale invariance. That's the first thing that this renormalization is telling you. But once you are there, the story only starts, because if now you assume that the fixed point is unique, then if you start from a rotated version of your lattice, for instance, and you iterate, you should end up to the same fixed point. So you should, by definition, in some sense, end up with something which is also rotation invariant. And if you start from a translation, you should also end up to the same fixed point. So you should not only get scale invariant, but also rotation and translation invariant. And if you do that, in particular, you realize that the spin-spin correlation, they necessarily get this form, that it's 1/a power of the L2 norm, of the Euclidean norm, which is not that obvious if you think about it. You are on a lattice, you could think that another norm, maybe the graph distance or something like that, is actually the relevant norm. What this heuristic justification is telling you is that it's the L2 norm that should come. And in fact, once you have Gaussianity and emergent symmetries, you end up with you can describe what is a fixed point, basically. You can describe all the large-scale behavior, you end up with what we call the Gaussian free field. And let me almost finish by the following observation, that in fact here, if you push one step further, if you start from another lattice, not with a square lattice, say, you start with another lattice, then you should also, when you iterate, end up with the same fixed point. So this is suggesting that whatever the discretization you are making, you end up with the same limit. It's called universality, and it tells you somehow that the details of your model are not mattering so much. The large-scale behavior of the critical system are the same. And this is something very reassuring from the point of view of statistical physics, is that yes, you are making assumptions. At the beginning, we made a few discretization assumptions, but they are not really relevant in the sense that you end up always with the same limit. So as I said, this limit in this case is called the Gaussian free field. So let me finish by saying, so the third recap, the moral to this last story, this last part of the talk, is that at criticality and large distances, you get emergent laws. We saw Gaussianity, for instance. We saw these symmetries. So basically rotation, scale, and translation invariance. There is actually a bigger one, which is called conformal invariance, but I will not discuss it here. So you get symmetries, Gaussianity. And the way, I mean, maybe the go-home message behind all of this is that, again, in order to get these symmetries to the Gaussianity in the paper that I mentioned, and in fact, these symmetries, we are closer and closer to get them in dimension 4, again, you use the connection between percolation and the Ising model, again. So there is a very strong kind of tool, which is a bridge that is connecting these two areas of statistical physics, and once you use it properly, you actually get all these emergent symmetries, and I don't remember, yeah. So just to conclude, let me tell you that this type of phenomena, they appear in many other contexts. So for instance, random matrices is a place where you have all these emergent laws and you have even universality, and all those things are understood, which is one of the great achievements of mathematical physics. In the case of the Ising model, it's still something which is really very much underway, but it's not there yet. But for random matrices, in particular, universality was a subject of great works in the past 20 years. And for people who want an example, maybe to kind of meditate on all these notions, there is actually the context of random walks. When you start from random walks and you look at large-scale properties of it, you always end up with Brownian motion. It's an example of a universality. You can start from different random walks. You will always end up with Brownian motion. And Brownian motion enjoys like scale invariance and properties that the actual random walk does not satisfy. So you end up here with an example that you can actually explain to master students of these emergent laws. So I think I will finish on that to let you meditate on this thing, and thank you very much for your attention.
Thank you.
Don't steal my fan.
Thanks, Hugo, for the very nice talk. We have a few questions from the audience.
I'm here live, you know.
Thank you. Hi. Thank you for the excellent talk. It's not a very precise question, but I was wondering, when you dealt with dimensions greater than 2 for the Ising model and developed these proofs, first of all, do they carry over to back to the d equals 2 case, and would that give you perhaps an indication of where and how integrability tools break down, and if there's really a no-go theorem, or if there's still some hope in d equals 3, or
yeah,
it's a bit vague.
Yeah, no, it's not vague at all. Usually when people tell you that, it's never going to be a vague question. You know. The worst thing you want is somebody telling you, I have a naive question, which probably means you are going to be like destroyed on spot. No, it's a very good question. So the technique does carry over to 2D. In fact, it's true on every graph. So, you know, here I'm trying to model statistical physics type system, but if you want neural networks or things like that, you want even to look at the Ising model on very different graphs, and this connection to percolation is always true. In 2 dimensions, it's especially interesting when you try to understand universality. Because there, actually, conformal invariance was proved by Stas Smirnov and Dima Čelkák. So there is a very good understanding of the emergent laws and so on when you have integrable systems. The problem is that, you see, take the square lattice and add just next to nearest interaction. Then it breaks integrability. So when the next to nearest interaction is small, there are ways of actually running renormalization type arguments. It's beautiful result, very intense one. But if you take like a next to nearest interaction, which is not especially small, then even if you are basically looking at a 2D system, you completely lost all the marvelous techniques of 2D. So there, we actually, for instance, use with Michael Eisenman, Simone Varzel, and Vincent Tassion, we use actually this connection to percolation, this random current, to prove that certain properties are universal for this. It's only the beginning of the story because it's a difficult actually theorem, and we would like to understand, for instance, conformal invariance. Yeah. And I think that harvesting this connection to percolation system is again kind of a robust way of approaching the thing, and it's very interesting in 2D as well. So.
Thank you.
Thank you. Anyone else?
Thank you. Thank you for the talk, and thanks for being here live. So the question is back to the model. When you started with the spin, the value was plus minus 1.
Yeah.
Is it studied? Well, could we make a new assumption where the values are minus 1, 1, or 0, and 0 would be that there's no particle.
Yeah.
No dipole.
Yes, so indeed you can change the space of spins. What you mentioned, for instance, adding the zeros, where you could think of it as a defect in your magnet where you don't have a spin, is actually called the Bloom-Capell model. It's a very interesting model. There are connections to the Ising model because it's still quite close in some sense. You can think of it as an Ising model on a random set, which is a set of non-zeros. And there are like very interesting results on it, and it's a little bit harder to study than the Ising model, but you have new phenomena. You have what we call a tri-critical point emerging, which is something that physicists are very much interested in. So this is a very interesting thing to do, this 0, plus or minus 1. Of course, you have also assumption. You could assume that the spins are valued in the circle or even in the sphere, which makes a lot more sense than plus minus 1, and you get different statistical physics models called the spin-ON models, which are also very interesting, that also have connection to percolation models, but which are, for now, a little bit more mysterious than what happened for Ising. So there is a whole like family and zoo of statistical physics model. I focus on this one to kind of give you an idea, but for instance, the Bloom-Capell is a very interesting model to study.
Okay, so if there are no more questions, I won't ask you a naive question. So
Thank you.
If there are no more questions from the audience, let's close this morning session by thanking Hugo again and all the participants and all the speakers of the morning who are still present, which is mainly you.